Welcome to the first part of Unit 3. In this part, I'm going to introduce the constant acceleration equations, talk about them a little bit, and then do a quick example. So without further ado, there are 4 constant acceleration equations. They can be derived using calculus. This class does not go there. I will discuss a little bit about where some of the terms come from and why they make sense. But I'm not going to try to derive them for you. So the first one relates the position to the position at time t equals 0 to the velocity at time t equals 0 times t. And then there's an acceleration term as well. So really quick, I'm going to make a list of what all these variables. Okay, so x is the position at time t. This is x naught. It is the position at time t equals 0. Okay, you'll see it in a minute. We will come up with a v. We haven't gotten there yet. This is the velocity at t. This is supposed to be the at symbol on all these other ones. I just didn't write it all the way out. So, and similar to x and x naught, you have v and v naught, where v naught is the velocity at t equals 0. And then lastly, we have the acceleration. Okay, and because the acceleration is constant, is valid for all times. Okay, if you look at this equation and you ignore the 1/2 at squared portion of the equation, okay, so ignore that last term for a minute, and then rearrange it. Maybe you need to do it on paper, maybe you can do it in your head. But if you rearrange it, you can see that you can get a formula that looks like a velocity is a change in position divided by a time. So the first 3 bits of this equation really are just the velocity equation, the velocity definition. And then we have to add to it a term that takes into consideration the acceleration. Okay. I'm not going to try to justify this last term at all to you. As I said, it involves calculus. But what I will say is that in a lot of ways, calculus is a study of slopes and areas. And with that in mind, if you think about the area of a triangle being 1/2 base times height, you have that factor of a half that pops up there as well. This 1/2 in 1/2 at squared is the exact same 1/2 that pops up in 1/2 base times height. Okay, same reason. Okay, there's the first constant acceleration equation. The second one relates the velocity at time t to the initial velocity plus the acceleration times time. Again, if you take this one and either on paper or mentally rearrange it, that one is just the definition of the acceleration. That's all it is, just rearranged. And v final and v initial have been replaced with v and v naught. But the idea is 100% the same. Okay, to get the third one, what you need to do is take the second equation, solve for t, and sub it into the first one. And that results in an equation for the velocity squared. Okay, so the velocity at time t squared equals the initial velocity, v naught squared, plus 2 times the acceleration times the change in position, x minus x naught. Okay, so there's your first 3 equations. The last one is for the average velocity. So v with a bar of it. Notice it's not an arrow in this case. It is a bar indicating average in the mathematical sense. And that is the sum of the 2 velocities divided by 2. Okay. Of these 4 equations, the top 2 are bread and butter. You use them all the time when doing projectile motion equations, calculations. The third one gets used, but not as often as the top two. That bottom one, I have only ever used when I have a problem specifically asking for an average velocity. But it's included, so I included it. I think you might have a homework problem that requires it. Okay. So there are your constant acceleration equations. If you look on your equation sheet, there are equations 4, 5, 6, and 7. I highly recommend that you write these equations down somewhere. Circle them on your equation sheet, whatever you need to do, because you're going to need them for the rest of this unit. Okay. So now let's work an example. Okay. We have a car slowing down uniformly from a speed of 21 meters per second to rest in 6 seconds. And the question is, how far did it travel? Okay. In the next part of this unit, I have a how do you solve these problems slide. I'm going to model it here so that you can see what I'm talking about when we get to that slide. So the first thing you should do is draw yourself a picture. It doesn't have to be pretty. It doesn't have to be, all sorts of detailed. It just has to kind of help you organize your thoughts. So what we have is we have a car. Okay, well, to me, a car is a box on wheels. So there you go, right? We know that it starts at a speed of 21 meters per second. So I'm going to let this position here be where it starts. Might as well make it 0 because I can, right? I'm going to let this be the t = 0 position because it's where I'm starting my measurements. And I know at this position that it is 21 meters per second with its velocity. So I drew an arrow for that. At some time later, I'm going to dot this guy in because obviously a car can't be in two places at once. I'm told it's at rest. It's slowed down to rest. So that tells me at this position, it's not moving. I want to know how far did it travel. So I'm asking for X in this question. So I put that in with a little question mark just to remind me, hey, this is what you're looking for. And it happened at a time 6 seconds later. So I'm going to include that information as well. Okay. Couple other pieces I need for a good picture. I need to define my coordinate system. So I'm going to define to the right as positive because that's the direction of my velocity. It's the direction of my motion. It's also traditional. We usually define to the right as positive. One last thing I need to somehow indicate the fact that this car is slowing down. It is accelerating. And because it is accelerating, I know that the velocity and the acceleration have to point opposite directions. So I'm going to put an arrow in here to indicate the acceleration is opposite of my initial velocity. I don't know how big it is at this point. So I'm just going to label it with a variable. That is A. Okay. So that's step 1. Draw a picture. Like I said, doesn't have to be overly artistically good, but it just has to help you organize the information in the problem. Once you have that, you write what I call a grocery list. And a grocery list is really just a list of what you know, what you don't know, and what you want to know. So I almost always put the variables in this order: X, X naught, V, V naught, A, and T. Okay. And now I can look at my picture and say, X is my question mark. X naught is 0. And you'll be like, but you chose that. Yeah, I chose that. Why shouldn't I choose it? I want to know how far it traveled. If I let X naught be 20, then the X I got would be 20 times, or not 20 times, but a factor of 20 bigger. It's not even the best way of saying it. So than what it would be if I let X naught equal 0. I would still get the same answer for how far did it travel, because really what I'm after there is the displacement. What's the distance between where it was at t = 0 and t = 6 seconds? I know that my final velocity is 0. I know my initial velocity in my coordinate system is a positive 21 meters per second. I don't know my acceleration, but what I do know based on my coordinate system is this thing should be negative. So I'm going to put a little note to myself there. Hey, it should be negative. And if I calculate something that is not negative, then I know I've done something wrong. And lastly, I know 6 seconds. Step 2 done. I've drawn my picture. I've written my grocery list. Step 3 is to look at those 4 equations and figure out a path to find the answer. Okay. There are 2 equations that involve the position. The first is the x equals x naught equation. The second is the v equals v naught equation. Oh, not that one. Sorry, the v squared equals v naught squared equation. Both of them require that you know the acceleration in order to find the value of the position. I don't know the acceleration, so before I can find the answer I want, I've got to find the acceleration. The equation I can use to find the acceleration is the second equation, so that's where I'm going to start. V equals v naught plus at. So 0 meters per second equals 21 meters per second plus the acceleration times 6 seconds. Solving this, I get a times 6 seconds equals negative 21 meters per second. So take a minute, look at that, make sure it all makes sense to you why I wrote it that way. So the acceleration is negative 21 meters per second divided by 6 seconds. And 21 divided by 6 is 3.5 seconds. Oh, not 3.5 seconds, 3.5 meters per second squared. And there's a negative sign hanging out in front. So now I know my acceleration. And indeed, it is negative. You can, at this point, write it into your grocery list so you have it as a parameter for future calculations. Now, you are back to, you have 2 choices to find your position. You can use the top equation, the x equals x naught equation, or you can use the v squared equals v naught squared equation. To me, it makes sense to use the x equals x naught equation because it's already solved for the variable you want, less likely to make a mistake. So that's where I'm going to go. Okay, so x equals 0 meters plus v naught was 21 meters per second times my time of 6 seconds plus 1/2 times negative 3.5 meters per second squared. I just ran out of room, so I'm going to write it down below, times 6 seconds squared. And if I take and put that into my calculator, I get 21 times 6 minus 0.5 times 3.5 times 6 squared. And I get a distance of 63 meters. Okay. Notice, had I chosen x naught equal 20, if I'd chosen to put my 0 somewhere else, then the answer I would have gotten here would be 83. I would have just added another 20 on. But that's not the question that this problem is trying to address. It wants to know how far did it travel. So if I did start it at 20 and calculated 83, I would then have to take 83 minus 20 to get 63 to tell me how far it traveled. So I might as well put my 0 where it makes sense to put the 0. Okay, this completes this example. In the next section, we're going to work a free fall question twice. The same question twice, showing how you can shift around your coordinate system and still get the same answer as long as you're self-consistent.